Welcome to this supplemental video for finding a sufficient statistic using the theorem for a family of exponential distributions. Okay? So suppose that we have this PDF and it's given by this function, and we could make this a PDF if we integrated across the correct integral or interval here. Okay? So let's just say that this is a PDF, and we're not worried about those limits because that's not the purpose of this video. So the first thing we want to do is we want to write f as a family of exponential distributions. Now notice that f is actually a family of distributions because every value of theta gives you a different distribution. So it's a family of distributions that's based on theta. Secondly, we want to use the theorem for the exponential family of distributions to find the sufficient statistic for theta. Okay? Now, what is it that we're trying to do? This is what we're trying to do. We're trying to put this in the form where we have an exponent and we have these three terms added together. Well, I can just say it once and draw a line. So they have to be in this function format. Now, this first term has to be a product of function of only x multiplied, or product of, with a function of only theta. So there can't be any mixing of theta and x. X has to be a function that can be separated from this, that's outside of this function of theta. It can't be like p of sine x, theta x or something where you can't separate them. Okay? So this has to be a function, p has to be a function of theta by itself, k has to be a function of x by itself, q is also a function of only theta, and s is a function of only x. Okay? So let's do that for our problem here. We've got f of x is equal to, now I'm going to take the exponent and then inside that I'm going to take the log of f. And f is, let me make sure, theta to the negative sine x times theta over 2 to the x minus 1. And then I use the property of logarithms. Log theta to the negative sine x plus, because it's multiplied here, log of theta over 2 to the x minus 1. And since I need to get this in terms of multiplied and added, I don't want things in exponent form because this is not a function of only theta, it's a function of x and theta now because you've got x to the exponent. So we need to be able to separate this out. So we need to use our property of logarithms to expand as much as we can. Whoops. So this is going to be, I'm going to bring the exponent to the front and multiply by log theta. Now this is starting to look like k of x times p of theta. But we're not done. Plus x minus 1 times log of theta over 2. Okay. Well, now I've got two functions of, I got a function of x times a function of theta and a different function of x times a different function of theta. So I can't combine these. So I need to keep going. I have theta divided by 2 in this log. So that means I can do a subtraction. exp negative sine x log theta plus x minus 1, and then parentheses, it's times all of this, log theta minus log 2. And now I need to expand it. Okay? And see if I can write it in the right format. because you can't always write it in the right format to be an exponential distribution. So I'm going to distribute x across here, and then I'm going to distribute -1 across here. And so this is going to be x log, use our parentheses, theta minus log 2 minus 1 times log theta minus log 2. I encourage you to use your parentheses and not be careless and make a mistake, because it will really cost you some points. So this is all about your algebra right here. So sine x log theta plus, now I distribute x across log theta and log 2. So this is going to be x log theta minus x log 2, and then minus log theta plus log 2. And all I need to do now is group and see if I can simplify in the right format. So I'm going to put everything that has a function of x times, and this is a theta, times a function of theta together, and then I'm going to put this by itself, and then I'm going to group these two together because they're both functions of x only. A constant log of 2 could be x to the 0 log 2. So it can be considered a function of x. Okay. exp, so negative sine x. Now notice that I have a log theta for both of these, so that can be factored out. And then I'd be left with negative sine x plus x, and this is times log theta. And then I have minus log theta plus log 2 minus x log 2. Again, I can factor out log 2. If I factor out log 2 of the first term, I'm left with 1. And then here I'm left with the negative x. So this is exp negative sine x plus x log theta minus log theta plus 1 minus x log 2. Okay. Now log 2 here is a constant, so now I really do have just a function of x, s of x. And this, that's clear that it is. And then this log of theta is my q of theta. And now this is my k of x, and this is my p of theta. Okay? In this case, p of theta and q of theta are the same except for a minus sign. Okay? And that can be, but they don't have to be. And so now f of x is an exponential family of distribution. Family of distributions. By the theorem for the exponential family of distributions, y equals the sum of k of x is equal, which is equal to, I'm going to rewrite this as the sum of x minus sine x, I can put the positive first, is a sufficient statistic for theta. It has to be this whole thing. You can't just take part of it. It's the whole thing. So it's x minus sine x, or negative sine x plus x, the sum of that quantity. Okay? So the sum of x is not a sufficient statistic in this case, not by this theorem anyway. And the sum of sine x is not a sufficient statistic. At least by this theorem, you can't say that it is. Okay? By this theorem, the only sufficient statistic you can say is the sum of x minus sine of x. That's the only thing. So I hope that clarifies this theorem. And let's look at what we did on the test. So on the test, we had the geometric distribution. And so we take the exponent of the log and we end up, some of you left it like this, x minus 1 times log of 1 minus p, plus log of p plus 0. Some of you didn't put the 0, but I don't think I counted off for that. So if you leave it in this form, your sufficient statistic by the theorem is sum of x minus 1, not the sum of x, but it's the sum of x minus n. When you're subtracting a constant like that, then that tells you you didn't simplify this well enough, probably. So you could make this better. So if you leave it in this form, then the only correct answer from the theorem is y is equal to the sum of x minus 1, or sum of x minus n. Because that's what it says. This is k of x. You have to take all of k of x. You can't just cherry pick what you want, just the x out of there. That doesn't work. Has to be the sum of all of that, and so of k of x. What you could have done is you could have continued like I did, because I don't want to use this as my sufficient statistic. That's going to be awkward to plug into things. So I could expand and say the x minus 1 I could distribute. So log of 1 minus p minus log of 1 minus p plus log p plus 0. And then I could group this together if I wanted to as log of, I've got p minus 1 minus p. So this is going to be p over 1 minus p. So I could do that. And then the sufficient statistic is the sum of xi. But you can only say that if you put it in this form, because the theorem says whatever this is, function of x multiplied by a function of theta, or in this case p, whatever that function of x is, it's the sum of the whole thing. In this case, it's just x. So many of you missed the points for this, even though you said the right answer, sum of xy, sum of xi is equal to y. You didn't use the theorem right. It was not obvious. It was obvious to me that you didn't understand the theorem, because if you had understood the theorem, you would have written this. Okay. Now, quickly, what is an example of a function that's not an exponential, a PDF that's not an exponential family of distributions? So earlier we had f of x equals theta negative sine x theta over 2 1 minus x, and we were able to write that in the right format for a family of exponential distributions. That was before. But now I've changed it slightly. Now I've made it 1 minus theta here, and you'll notice that x is in the exponent of that function. In fact, it's in the exponent of both functions, and this is going to prove to be challenging. Let's see what we can do. So this is going to be negative sine x times log theta. I'm just going to skip the step where I write it as a log to the exponent. I know that this exponent's coming down in front of the log, right? So this is going to be plus 1 minus x log of 1 minus theta. Now, I need to expand quickly. Negative sine x log theta plus or minus x log 1 minus theta let's see, plus log 1 minus theta. I just expanded this, okay? And so plus 0 for the x only term. Well, I have a problem. This and this are not the same. I can't factor them out. And this and this are not the same, so I cannot factor them out. There is no way that I can write this as a function of only x times a function of only theta, p of theta. There's no way to do it. I can't combine it that way because this is 1 minus theta and it's inside a log. There's nothing I can do. And no, it's not equal to log of 1 minus log of theta. It is not that. So please don't do that. That's terrible, terrible algebra. We'll get you many points off for doing that. Okay? So this is not an exponential family of distributions. So it's very similar to this one, but it's different enough to where it's not. So not everything is an exponential family of distributions. So if it is an exponential family of distributions, this theorem is great. If it's not, you have to go back to the factorization theorem. All right, I hope this has helped explain this topic more thoroughly and wish you all the best of luck on the final exam.